Hello, this is Mr. Collier, and today we're going to be looking at some rational functions with oblique asymptotes. Okay, and this happens when we have a quadratic over a linear. Right, so oblique means your asymptote is not going to be horizontal or vertical, it's going to be like diagonal. So let's sketch this function, and first thing you might want to notice is the denominator is just x. So that means when x equals 0, we're going to have a vertical asymptote. And to get the oblique asymptote, what we do is we want to look at what happens as x goes to infinity of the function. And it'll approach a line that's not horizontal or vertical. Okay, in order to do that, we're going to do long division. So you'll see why in a second. To do the long division, well, it sort of looks like regular long division with numbers. So you do 6 into 14 goes 2 times. 2 times 6 is 12. 6 goes into this 4 times. 4 times 6 is 24. You get 3 remainder. So that means 147 divided by 6 equals 24 plus 3/6. Right? That's how it works. And we can do the same thing with algebra. X into x squared. Now, if it's x squared plus 1, well, actually, for this one, you don't even need to do long division, because you can actually just divide both terms by x, and we have x plus 1 over x, right? So that's the function. You see, as x goes to infinity, this becomes closer and closer to 0. So we just get y equals x. So y equals x is the oblique asymptote. Okay? And that means as x goes to infinity, we get closer and closer to the line y equals x, which I'll just draw here. Okay, we get the x-intercepts and y-intercepts here, and then we graph it. The y-intercept doesn't exist, right? Because you plug in x equals 0, we get undefined there. So the x-intercept is going to be 0 equals x squared plus 1, which also doesn't exist. Okay, so now the graph is going to probably look like this or this. Maybe you want to just plug in a point to see where it's going to be. If we plug in x equals 1, we get 2 over 1, we get 2, right? So that means the point 1, 2 is on the graph. So the graph of the function is going to look like this. And we have a similar shape on the other side. It gets closer and closer to these asymptotes, right? So remember this long division. Now we're going to do that for the next one. We're going to do, let's do it over here. X plus 3 into x squared minus 6x minus 1. And this, so if you want something to multiply by this to give me x squared, then there's got to be an x. X times that gives you x squared plus 3x. Then we subtract, just like regular numerical long division. We get negative 9x, bring down the 1 to negative 1. And we want to get a negative 9x here, so we need a negative 9 to multiply by this to give you a negative 9x minus 27. And remember, we're subtracting, so be very careful. We're going to get a positive 26 remainder. Okay, that means this function is the same as, so if we divide these two things, we're going to get x minus 9 plus the remainder is 26. We get 26 of these remaining, right? So this is going to approach 0 as x goes to infinity, so the oblique asymptote is just going to be the line y equals x minus 9. The vertical asymptote we can see here is going to be x equals negative 3, and then you can get the x-intercept and the y-intercept the regular way, right? So vertical asymptote negative 3. You got y equals x minus 9, so you got to go down to 1, 2, 3, 4, 5, 6, 7, 8, 9. And draw a line here, right? So you get the x-intercept, but you have to use quadratic formula and stuff like that. So if you want to figure out where it is, well, the x-intercepts will tell you. What's the y-intercept going to be? The y-intercept's pretty easy. That's going to be negative 1/3. Okay, so it's going to be down here. Okay, the x-intercept would probably get one right here and one right here with the quadratic formula. Anyway, I'm not going to do that right now, but the graph's going to sort of look like that. Then you have a similar shape on the other side. Okay. It says to label everything, so I should probably do that. Y equals x minus 9. That is 0, negative 1/3. And this is x equals negative 3. And if you get the x-intercepts, you should label those as well. Okay, same thing in the next one. We're going to do long division, x minus 6 into x squared plus 6x minus 4. So you need an x here because x times x gives you x squared. Remember, we're subtracting, not adding, so you get 12x minus 4. So you need this to be a 12, and 12 times that gives you 12x minus 72. And when you subtract, you get 68 remainder. So that means the function equals x plus 12 plus 68 over x minus 6. So when I go to graph it, the oblique asymptote is going to be x plus 12. 12. And the vertical asymptote is x equals 6. The y-intercept, plug in 0, you're going to get 2/3. So 2/3 is going to be down here somewhere. You get the x-intercepts again with quadratic formula. So the graph's going to look like that. Right? The last one's a bit tricky. There's no x term here. So when that happens, you got to insert 0x. Okay. So again, we need an x here. And x times that gives you x squared minus 5x. Subtract and you get positive 5x. Okay. And then we need a 5 here, so this is going to be a plus 5. And that's going to give you 5x. Multiply by that, you get negative 25. Remember, we're subtracting, so it's negative 12 minus negative 23. We get 13 remainder. So that means the function is x plus 5 plus 13 out of x minus 5. Okay, so the oblique asymptote is going to be y equals x plus 5. The vertical asymptote is going to be x equals 5. The y-intercept is going to be, plug in x equals 0, you get 12 over 5. Okay, which is about 2.4. And the x-intercept we can get this time. It's pretty easy. You're going to have x squared minus 12 equals 0. So x equals positive negative root 12, which is 3 point something. So let's do that over here. So we got x equals 5. We've got y equals x plus 5. Okay, I should have probably planned ahead a bit better to make some more room up here. We got the y-intercept is 2.4. The x-intercepts are positive, negative, that's about 3 point something. Anyway, it's going to be like here somewhere. So it's going to look like that. Okay, and there's going to be a similar part up there.